Hello everyone, I'm very happy to have Divesh Aggarwal speaking with us today. As you just like the Shara, Aggarwal is something that you can spell in many different ways. But for the purpose of this talk, this will be the official spelling of Aggarwal. Divesh is visiting us from the National University of Singapore. He is here for the entire week, so you can meet him today, tomorrow, or Friday. Thursday, he is at IIT Bombay, so then unfortunately you cannot unless you go there. He'll be talking about his work on the integers unbounded subset sum problem. I think the title is changed. But yeah, yes.
Thank you very much for the introduction. That spelling is because my dad is from Punjab, and that's where like basically they pronounce it slightly differently, and that's where they spell it like that in most of India. Yeah, okay. Thanks a lot. This is my first time visiting TFR. Very happy to be here. Thanks for the invitation. So today I'll be telling about this result in polynomial time algorithms for integer programming in the total regime. This is my first time giving this talk. I mean, it's a very recent work. Joint work with Anton Liu, Miklo Santa, and Carol. I'm not going to pronounce that last name. Yeah. Whatever I'm going to talk about is going to be quite simple. Ask as many questions as you like. If something is not clear, it's my fault, not yours. So ask. Okay.
Maybe you just have to open the Acrobat screen, probably.
Sorry.
Just click on this. Click on what?
The Adobe screen at the bottom.
Oh, okay. Oh, I see. Okay. Yeah. Yeah. Okay. So outline of my talk. I begin by talking about algorithms for the unbounded subset sum problem. If you don't know what that problem is, we'll just get to it in a moment. Where the target is far. And then I talk about the obvious generalization of this problem to higher dimensions and give a very simple reason why it does not work. Then I talk about like a sufficient and natural condition for a polynomial time algorithm for integer programming. So this is an alternative generalization to the unbounded subset sum problem that actually does work and gives us a sufficient and natural condition for in which you can get a polynomial time algorithm for integer programming. And then we show that the condition we obtain is necessary in a certain sense, and I'll say more about this as we get there. Okay. So the unbounded subset sum problem, you might have heard this in the name of coin table problem also. So it's like given numbers a1 to an, so positive integers, and a target number t, all of them are non-negative integers. So we look at, so think of them in the sorted order. So a1 is less than a2 is less than an.
So that is distinct?
Huh?
That is
distinct, yes. Because, I mean, you've seen a moment why it doesn't matter. I mean, it's without originality, they're distinct. Because if they're the same, we're talking about like basically repeating them as many times as we want. So if they're the same, it doesn't really help us, right? So the goal is to find non-negative integers x1 to xn such that summation AIXI is equal to t, which is basically since like repeating a1 x1 times, a2 x2 times, and so on to get t, right? Or we want to decide whether there's no such solution. This is known to be NP-hard. You can contrast it with the more well-known subset sum problem, where it's basically you're only allowed 0-1 combination. So each coefficient is either 0 or 1. It means you select that AI or you don't. Here you selected x1 AI, you select xi number of times. Still an NP-hard problem. Actually, there's an easy reduction from subsets after this. Okay. So unbounded subset sum within the target is far off. So Erdős and Graham basically studied this problem back in 1972, and their result was improved by Dixmeyer in 1990. So what the results together basically show is that if the target is pretty large, it's like an minus 1 times an divided by n minus 1. So think of it as the largest number squared divided by n, roughly that, right? And the GCD of a1 to an divides t, then there exists a solution. There always exists a solution if this promise is satisfied. So notice that the GCD a1 to an divides t is a necessary condition, because if that would not hold, then obviously there cannot exist a combination of a1 to an that adds to t, right? And intuitively, it kind of makes sense that if T is very large, then it's easier to find such
The
exponent.
GCD division condition is not sufficient because you want the weights to be positive.
Right, right. If you were not interested, if you were happy with any solution, then Euclid's algorithm would just give you an answer, basically, as long as GCD divides T.
Also, this condition, it's not really linear. So if you scale everything up, then it becomes hard to satisfy the condition, right?
If you scale everything up, then
By some factor,
yes.
then
The T.
No, you will also scale T, right?
yeah, so that side scales by something linear, that side scales by quadratic.
Right. So
this
that is true. But okay. But what you can do is you can so this original condition was actually stated with the assumption that the GCD is 1.
I see.
But because you can just divide everything by whatever you scale up,
Yeah.
right? I mean, this doesn't make the problem any different essentially.
Yeah.
So I didn't write that GCD is 1 because basically GCD being larger is only going to help.
Yeah.
Okay.
No, but it may violate that condition. If you scale it up, then
The first
GCD
condition, right? Yeah, so you want the.
Yes, so but then you can reduce it to a problem where this condition can be satisfied.
Yeah,
Just
I know. I'm just
Okay, so the condition, so it's not a necessary and sufficient condition, but it's a sufficient condition. Sufficient condition.
Yes.
Okay. So the condition is nearly tight. For example, here's a simple example to show that the condition is nearly tight. I'll just show it for n equal to 2. So let's say A1 and A2 are co-prime, and the target is something like this. So A1 times A2 minus A1 minus A2. If you want to express this as an integer combination of A1 and A2, by looking at this equation modulo A2, what you'll see is this will vanish, and this will vanish. So you will have A1 x1 is congruent to minus A1 mod A2. So in particular, this will give
X1 is my co-prime, so A1 is 1.
sorry, actually, x1. So x1 is congruent to minus 1 mod A, right? So you get x1 is congruent to minus 1 mod A2, right? Because A1 x1 is congruent to minus 1 mod minus A1 mod A2. So x1 is congruent to minus 1 mod A2, which basically gives you x1 is congruent to A2 minus 1.
This is for 2. This is also what Frobenius found.
Yes, it's exactly that.
Yeah.
If you're familiar with Frobenius, this is exactly what I'm saying.
But then this is the smallest rate for 2.
Right. For 2, this is the
largest, which is not possible.
This is the largest, which is no, or the smallest, which is not possible.
No, the
largest, which is not possible. Yeah, if you go one bigger than this, then you can get it. Right. So x1 is A2 minus 1 mod A2, and similarly x2 is A1 minus 1 mod A1. And the smallest positive numbers that you can pick, basically, that satisfy this are x1 is equal to A2 minus 1, and x2 equal to A1 minus 1. But if you take those, then this will already be much bigger than this. So this will look like 2 times A1 A2 instead of A1 A2, right? So that's just not possible. So in particular, means that this shows that this, if the target, so here the target was closest to A1 times A2, so which is exactly what we had here, so slightly less than that. This really shows that this condition is almost tight, basically. And they actually constructed a general example for large networks. Okay, so this work, what we look at is a polynomial time algorithm for this problem, for the unbounded subset sum problem. When this condition is fulfilled, actually we need a slightly stronger condition. We need that t should be bigger than ai minus 1 times ai divided by I minus 1 for all I. So not just for the largest two, but for each of them. So this is like slightly stronger. I mean, if all the numbers were roughly equal, then this would like basically be a factor n stronger, right? Roughly. But then the instance should be easy for other reasons, right? So it's morally kind of similar to the Kurdish condition, and so we need this condition for our algorithm. And like the GCD condition, obviously, so I should fulfill the GCD of A1 to AN divides T. If both of these conditions hold, then we show there is a polynomial time algorithm.
So there is a polynomial time algorithm to find the x.
Find the x. Yes.
Okay.
Yes. Okay. Yeah, for unbounded subset sum, yes, exactly. Find the x. right? So here's the algorithm. It's a pretty simple greedy algorithm that we have. So let xn be the smallest non-negative integer such that, I mean, basically we choose xn to be the smallest non-negative integer such that, let's say g is the GCD of a1 to an. So we want that this GCD should divide t minus an times x. So this is a necessary condition that we must have, right? I mean, we choose xn to be the smallest positive or non-negative integer, so xn must be basically less than g, and to satisfy this, there will be a unique xn which is less than g, and it should satisfy. And then what we do is we recurse on. So now what we are left with is t minus xn, an, xn, and a1 to an minus 1, and the GCD of all these numbers is g. So we just divide each of these numbers by g, and also divide t minus an, xn, the target, by g, and we recurse. This is exactly like what the kind of thing that we were talking about. So we can just divide everything by g, and we are left with these numbers a1 prime to an minus 1 prime, and the target, right? And to prove that this works, it's sufficient to prove that the condition that we wanted to would still hold, like this, which is basically for every I, this new target divided by ai minus 1 divided by g, the new ai minus 1 times ai divided by g, the new ai. This is at least the original ratio. So of t divided by ai minus 1 times ai. If that holds, then basically if the condition was earlier fulfilled, then my induction basically would get fulfilled. And it's easy to check that this holds. So I just proved this. So equivalently, it's sufficient to prove if you just simplify it. There's a g squared here and a g there. So you get g times t minus a and xn is greater than or equal to t. ai minus 1 and ai cancel. So you get just g times t minus a and xn is greater than or equal to t. And this just simplifies to t times g minus 1 is greater than or equal to g times a times xn, which is true because, first of all, xn we chose to be a number between 0 to g minus 1, because it was basically a subnumber modulo g. So it's in particular, it's less than or equal to g minus 1. So xn less than or equal to g minus 1. And g times an must be less than or equal to an times an minus 1 divided by n minus 1. So why is that?
Everything is divisible by g.
Everything is divisible by g, and they are distinct. So an minus 1 is at least the n minus 1th multiple of g, which is n minus 1 times g. So basically, so g times an must be less than or equal to an minus 1 times an divided by n minus 1, which is at most, which was our starting condition. So basically, so our condition is fulfilled, which means by induction, we get that this algorithm works. So this was the first result. It's quite simple to describe. It's a simple greedy algorithm, shows that the early clamp condition, like basically, can almost be converted into an algorithm. So it's like, yes.
Can we go back to the previous slide?
Sure.
Find the smallest non-negative integer such that equals to the
GCD is the GCD of, so G is the GCD of the first n minus 1?
First n minus 1. Yes. First n minus 1.
Not there.
So basically, we want to choose this so that this would still be a valid target, right? I mean, that condition would still be fulfilled, right?
Originally it is.
Yeah, because I mean, the new target would be t minus a and xn. This would be valid as long as the GCD of the remaining ones divides the new one.
So why won't I end up choosing xn equal to 0?
If the GCD was 1, then you would choose xn equal to 0.
So even if g may not divide t.
G might not divide t, no? If then you would need
first
to.
n minus 1. Oh, I see.
G is the GCD of the first n minus 1.
Okay.
Not all of that.
Okay.
Right? So
There's something, so the denominator also changes, right? You have to show that t over ai minus 1 is larger than 1 over I minus 1. And you only know it's larger than 1 over I for the previous from the previous.
No, but that's in the next slide.
G minus
Just go to the next slide.
yes.
So you get that this is at least t over.
So this is a new ratio of t prime divided by ai minus 1 prime times ai prime.
Yeah.
which is at least the original ratio.
Oh, I see. Okay.
And we wanted, and remember that we wanted that all of them are, so this ratio we want to be basically bigger than 1 over I minus 1.
Yeah.
It was bigger than 1 over I minus 1 earlier, it still
Okay.
stays bigger than.
G could divide AN also, right?
G could divide AN also.
Then how will you, then T minus?
XN would be 0.
Then Xn would be just 0,
Oh, okay.
which would trivially satisfy the condition.
You want to take as few of the largest point.
Sorry?
You want to take as few of the largest point as possible.
Exactly. Yeah. So it's like it's the greedy algorithm where we pick the fewest possible largest point and then continue. And we're showing that that condition basically enforces that this works. So, questions? All right. So now I want to talk about the generalization of this problem. So I'll take a slight detour to talk about integer linear programming, and you'll immediately see why this is a natural generalization. Okay, so the integer linear programming, probably everyone in this room is familiar with this problem. So you're given vectors a1 to an in some d dimension. So let's say integer vectors and a target vector t, which works in z to the d. You will find non-negative integers x1 to xn such that summation ai vector xi, so x1 times the first vector plus x2 times the second vector and so on, is upper bounded by t vector. Where I'm saying when I'm using this inequality, I mean each coordinate should satisfy the inequality, right? You can think of this as basically d different constraints, and you want an integer set of integer point that satisfies this constraint. So this is a typical picture in 2 dimensions where each line corresponds to a constraint, and this is the feasible region, and the goal is to find some solution in this feasible region. This is the feasibility version of the integer programming problem. If you can talk about different variant, but here I'm talking about the feasibility version. And now an alternative version of this problem is where all the inequalities are just equalities. So you're given a1 vector, an vector, and t vector in z to the d. The goal is to find x1 to xn such that this is equal to t.
Shouldn't you call it ILP without inequalities instead of ILP with inequalities?
Because I'm hearing all of my these are inequalities. This is the standard version, and here I'm talking about all of them.
No, but if you what? If you put a negative sign there, it can make it into equality. Right?
Yeah, just coming to that in a moment. But like let's just think of everything there as inequality, everything here as equality. And I'm going to say in a moment that it doesn't really matter. Basically, both.
You know, my point is this sounds more general. Like it's ILP with
yeah. So
actually weaker.
I'm
It's ILP
saying that
without.
both are equally general. This is what I want to say. They're essentially the same problems, right? So this problem, if you notice, this looks very similar to the unbounded subset problem. Some problem that we just talked about. It's just a generalization of that too.
Wait, do you just add one variable?
Yeah,
make it
it's
equal?
Right. So the two problems are equivalent. So the two variants I talked about just now are equivalent. So if you had the inequality version, you could simply just introduce new variables u1 to ud and then write these equations as summation ai vector xi plus u plus the vector u. So this is just the u1, u2, ud vector is equal to the target, and this is as long as there exists x1 to xn and u1 to ud non-negative integers. So that this holds, we have a solution, right? So this you can see if we could solve the equality version, we will be able to solve the inequality version. And for the other reduction, you have this constraint. You can just introduce inequalities, which are like AIXI less than or equal to t, and negative of solution AIXI less than or equal to minus t, which is equivalent to AIXI greater than or equal to t. Together they will imply this. So by just doubling the number of constraints, you can basically get that. So both versions are equivalent. We'll be working with this. Basically, the equality case, because this is very similar to the problem that I just talked about. Okay. Questions? All right. So we want to talk about ILP with equalities. So given a1 to an vector and the target vector t, the goal is to find non-negative x1 to xn such that x1 times a1 vector plus x2 times a2 vector and so on is equal to t vector. Okay. So if we want to generalize our approach that we had for the unbounded subset sum problem, we need a few things. First of all, we need an interpretation of GCD for vectors, right? There's no GCD for vectors, right? But like we need something that would play the role of GCD for these vectors, right? And a reasonable notion of a large/distant target, like basically, so there we had the Dish-Graham condition, which is like the target is very large. What would large mean for when we're talking about vectors? These are two things that we want to understand. So we go one at a time. Let's talk about the first one first. So I'll take a detour, talk about a lattice. What is a lattice? A lattice is a discrete subgroup of R to the D. Think of integer vector v1 to vn. So a lattice is all possible integer combinations of these vectors v1 to vn. So think of y1 times v1 vector plus y2 times v2 vector and so on plus yn times vn vector, where y1 to yn are integer. So for example, here you see a picture of a two-dimensional lattice. Let's say this was one vector v1, this was another vector. So you can see that like the lattice vectors are just basically all integer combinations. So let's say 2v1 is in the lattice, v1 plus v2 is in the lattice, 2v2 is in the lattice. So it's like taking all integer combinations of these vectors. That's the definition. And so what would this be if these vectors were scalars, if you were talking about one dimension? So the lattice would be all integer combinations of these scalars v1 to vn, which is just z times the GCD of the n numbers v1 to vn. In d dimensions, GCD is analogous to finding a basis of the lattice. So a basis, what is a basis? A basis is linearly independent vectors u1 to ud such that the lattice generated by all integer combinations of these n vectors is the same as the lattice generated by all integer combinations of these d vectors. So these d vectors are kind of, in some sense, representing all integer combinations of v1 to vn. Right? And in a very famous result by Lenstra and Lovas from 1982, they showed how to basically build a basis given any set of vectors. Right? Actually, if you look at different write-ups of this LLL algorithm, you might not exactly find that it finds the basis, but it talks about given a basis, you find a good enough basis and so on. But actually, you can even interpret that result to basically show that it gives you a basis given any arbitrary set of vectors v1 to vn. So once again, what we get is d vectors linearly independent such that the lattice generated by these vectors.
What does linear independence mean here? Because you don't.
Linearly independence is just the standard linear independence in the real sense.
Okay.
Right? But now here when I'm saying all integer combinations of these d vectors is the same as all integer combinations of these n vectors. Right?
Okay.
So for example, d equal to 1, we found one number which is a representative of all integer combinations of these n numbers. Right? We basically take all integer combinations of this number, the GCD, we get all integer combinations of basically v1 to vn.
Yep.
Is it real such a basis always exists?
So if you think of these vectors as integer vectors, then it's straightforward that the basis always exists. Because it's a subgroup of z to the n.
Okay.
Right? Yeah.
I mean, what is not true is that the u1 through ud need not be a subset of v1 through d.
No, that's
Not to even in the 1D.
Yeah, that's true. I mean, I said that it's not the linear independence. You can always find a subset of your spanning set.
yes.
Oh.
Yeah, we're not looking for arbitrary linear independent, but like it's finding representative linear independent d vectors, right? And that would basically generate all vectors in this. Okay. Any questions? Okay, so everyone? Okay. So, okay. So now, I come back to the problem that we were talking about. So we are talking about integer linear programming with equalities. You're given n vectors a1 to an and a target vector t. And the goal is to find non-negative x1 to xn such that summation x1 times a1 vector plus x2 times a2 vector and so on is equal to this target vector. So based on what I just talked about, I conjecture that there exists a solution. If now I replace the GCD condition with the obvious generalization, this target vector is in the lattice generated by these n vectors a1 to an, right? And so that takes care of my GCD condition. So that seems fine, right? Then I want something about the target being far off. So what about I choose that I say that each coordinate of vector p is larger than some number m. It's like very large. So think of m as some very large number, and then I say that each coordinate of t is larger than some m. So we played for a while with this, and then realized that and it just is not possible. And we had complicated examples until we had like some very simple examples. So I'll give you something very, very simple why it does not work. So think of like just two vectors. The first vector is 1, 2. The second vector is 1, 3. Right? And let's say the target is mm. Like no matter how large m is, you cannot find a non-negative combination, integer combination of these two that would give you this. Because no matter what you do, the second coordinate would be larger than the first coordinate, right? I mean, this is clear. This is very clear. Although the lattice generated by these two is the entire Z2. So you can get all integer vectors if you just take all integer combinations. But in particular, this can be also generated, but you will get like, I guess this times 3, m minus this times 2. No. Sorry, no, this times 2, m minus this times m. Okay, that will work. Okay, that will give you this vector, but you cannot have a negative integer combination. That gets you m, right? So
Is the so there was a largeness criteria in the Erdős-Graham statement. And you had a largeness criteria in your algorithm, which was slightly strong.
yes,
And the proof of that was almost inductive the way you build up the algorithm.
yes.
Is the proof of Erdős-Graham also
Not really, and actually the Erdős-Graham condition, I can talk about that in like towards the end or like, but the greedy approach will not work if you did not have the additional condition that we, right? The greedy approach will not work. In particular, if you want, I can just if you like the Erdős-Graham condition says basically that the target is bigger than an squared divided by n minus 1. Notice that if you introduce some number, some new number, then the condition becomes stricter. So you introduce a smaller number, then you suddenly increase n, the condition becomes stricter. Although the greedy approach does not change, at least with respect to the large AIs, right? So it's not clear how to make that work without the additional condition.
Yeah, I mean, what I was wondering is when you had the conjecture,
Yeah.
it seemed a bit too strong to me.
Okay.
But then I felt that, somehow the one-dimensional version also seems a bit strong, but that is true. So,
Okay.
you probably don't have the right window.
Yeah, but I mean, so we played with this. We thought that maybe something like this would work. I mean, that would be a natural generalization. We had plenty of ideas. We were trying to prove that this works, and then came up with our counter examples, right? Okay, so it was not so straightforward, even though it looks quite stupid that we have found something as simple as this.
So does it work for instance, if there are 3 vectors in two-dimensional library?
No, you find counter examples no matter what you do. Like basically, this is not the right condition.
You can put 1, 2, 1, 3 and 1.
This is
Still.
this is just not the right condition. Like basically, this is it's not.
If you're looking at just positive integer linear combinations, you're looking at instead of the lattice, you're looking at some cone.
Yeah.
And you can't just the cone. If you can't just say that if you're outside of a rectangle, you'll leave the cone.
Yeah. Okay. So here's what we actually prove. So I'll go slow with what we're saying. So the same problem, we've given A1 to AN vectors and the target, and we want to find integer, non-negative integer combination of these vectors that adds to the vector. So the first condition is this, like the target is in the lattice generated by A1 to AN. And so this is a convenience thing, but like this is easy to get. Like let's say the first D vectors are linearly independent. We can just use Gaussian elimination to essentially get the first D vectors. We can just rearrange the vectors so that they are linearly independent. Just
Do you want dependence or independence?
sorry, linearly independent. Sorry, I meant to say linearly independent. That's it. I don't know. Yeah. Sorry, I meant that they are linearly independent. So, and there exist y1 to yn reals. So now we are saying that there exists a real solution such that the last n minus d of them are bigger than 0. And the first d are large enough. Such that this condition holds for this real, these y1 to yn. So instead of the largeness condition we are talking about is now slightly different. So we're saying that there exists at least a real solution where, so you could think of it as like basically the real solution with all coefficients large. But actually what we need is really the first d of them are large and the rest of them are just non-negative. Right? So for now, I mean, this might seem a little bit strange why we are having a different condition for the last n minus d and the first d. For now, you can think of it as like, basically, we just have a real solution with all the coefficients are large.
Your norm is 1 norm or 2 norm?
Sorry?
This is a 2 norm?
This is, I mean, up to a factor square root n, it doesn't matter, but we're talking about 2 norm. Yeah.
You're saying there's a large solution.
Yeah, large real solution. Yes. Then there exists a, then we can actually find a non-negative integer solution. That's what we are saying.
But some.
Okay.
You're also disallowing equalities, right? Y d plus 1 to n cannot be 0.
Oh, I should have said greater than or equal. I should have said greater than or equal. No, I really need greater than or equal. It's not disallowing equality. That's a good. Yeah. And the paper is greater than or equal to, I think, in the top. Okay. So I'll mention the algorithm without the proof of correctness. The proof of correctness goes on similar lines. Of course, uses more about lattices, and I don't want to get into that. But like the idea is similar to the simple proof that I described for the one-dimensional. Okay, so what's the algorithm? So first of all, you use linear programming. So we know that linear programming can be solved in polynomial time. You can use linear programming to find y1 to yn that satisfy our condition. So it's like find y1 to yn such that these yd2 plus 1 to yn are greater than or equal to 0. So this should be greater than or equal to and y1 to yd are bigger than this number, and summation ai by n is equal to 0. So note that we have, this is a solution, a real solution, which is large, right? Large positive or large non-negative. Okay. So what we do?
So that also requires. So if that is greater than, then you do some kind of, because linear programming cannot solve strict inequalities. So you have to search, and there's some limit on the epsilon here. Oh, they're also greater than equal to.
So everything is everything is greater than equal to. That's why this actually stuff. But like all of them should be greater than equal to. Okay. And then okay. So let's say let zi be yi minus its integral part, so fractional part of yi, right? And we write the target vector, so let's say t prime is just zi times ai vector. So it's like this, which is just the target minus the integral part of yi times ai, summed over I equal to 1 to. So notice that this vector is in the lattice generated by a1 to an. Simply because these are all integers. Right? And also we know that these are large. Yi's are large, right? And larger than that now. Okay. So now what we are going to do is we are going to find an integer combination of this, we're going to express this as an integer combination of a1 to an, and then hope that like basically because we have something large to help us, so when we add up the two, we'll still get something that is non-negative. Okay. So the way we do it is, for I is equal to n to d plus 1, we just find the smallest non-negative xi prime integer such that the star t prime minus whatever we have found so far, xn prime, an prime, an, so on, plus xi prime ai is in the lattice generated by a1 to ai minus 1. So in particular, the first step would be you find the xn prime such that t minus xn prime an is in the lattice generated by a1 to an minus 1, just like what we did in the one dimension. And we just did, when we get the next one, we just take that xn prime and then get xn minus 1 prime again, so that the target vector, the remaining target vector, is in the lattice generated by a1 to an minus 2, an minus 2, and so on.
So there's the same problem with one less variable.
Right. So we just do this for n to d plus 1. Of course, since we are choosing this to be the smallest non-negative integer, obviously these are all positive. So remember that like y d plus 1 to yn, well, we don't really need them to be large. We just needed them to be non-negative because basically we are getting something non-negative here. And then what will be left with is to find x1 prime to xd prime. Notice that it's still in the lattice generated by a1 to ad, and now they are d vectors linearly independent. So we can.
So how do you find the x in 3, x prime r?
Yeah, that's the step that I did not describe, but like basically it's kind of you find the basis of the lattice, and then it's not that hard to actually find that. But I didn't want to get into basically how you find, but it's really not I would have to introduce a lot of lattice terminology if I would like to do this. But the idea is very simple. Like I mean, how do you find number basically more that t minus a and xn is a multiple of GCD? It's very simple, just in higher dimension. Yeah. So then once we have found all these and xn prime to xd plus 1 prime, we can use Gaussian elimination to find the remaining, because now we are in d dimension. We have d linearly independent vector, and we have a vector that's in the lattice generated by these d vectors. So obviously there's a unique x1 prime to xd prime, which such that this d prime is, and since it's in the lattice, those x1 prime to xd prime that we'll get will be integers. Basically, that we have promised this. So you can just use simple Gaussian elimination to find these x1 prime to xd prime, and then for I equal to I 1 to n, we have that xi is just xi prime plus the integral part of yi that we had earlier separated out. So that's our final answer.
Or you're just using the fact that the solution is unique, so we'll integers.
So yeah, so these are just unique, easy to find. This doesn't take. So when you are just left with d, then it's easy to find.
And this is the bound on the denominator of Gaussian, I assume, something like that.
Yeah, this is basically the bound on the volume times n minus d. So you will essentially the volume of the lattice. So this is like the fundamental parallelepiped of the lattice. So this is a bound on this volume. So you would always not. I mean, the contribution from any of a1 to ad will not be more than the volume essentially, and you will be doing that n minus d times. So you basically have that n minus d times that volume. So that number, right? And we choose xi to be xi prime plus yi. And it might seem like we are throwing kind of like pretty big number, and so it's easy to find a solution. But actually, I'll just show an example to show that bound that we have there is kind of tight. So if you go a little bit smaller than that, then there might not exist any solution at all. Okay. So here's the example. As I said, I'll finish early. So the example, let's say P1 to PD plus 1 are distinct primes. So the first vector is P1 0 0 0 0 0. The second vector is 0 P2 0 0 0. So it's like so on. The dth vector is 0 and PD. And the last vector is the D plus 1 prime in all components. Okay. And this target. So what we are doing here is, so we are multiplying all of the primes, D plus 1, and minus P1, minus PD plus 1, that's the first coordinate, minus P2, minus PD plus 1, this is the second coordinate, and so on. Might seem a little strange, but you'll see in a moment why this is a good example. So obviously, if we wanted to find a real solution, there is a large positive real solution y1 to yd plus 1, such that y1 times a1 vector plus so on is equal to this. So you can find large positive number. You just pick a large positive number here plus something here. So pick a large number here, and then you're still left with something large. But it's not that hard to actually find large y1 to yd plus 1. That
You don't even need yd plus 1, that you can just have the first one.
For 1 to d.
Yeah, so put 1 to d. Yeah.
yd plus 1 equal to 0 also.
Yeah, so you can just actually this exactly. So you can just do yd plus 1 equal to 0, and then you just get y1 equal to something large. And you can get quite large. Like basically that will be P1 times whatever. This divided by P1. So quite large. So think of all of these primes as roughly of equal size. Right? But distinct prime but equal size. Okay. So they exist large positive C solution, and also it's not hard to see that this target is in the lattice. In particular, this would generate all vectors, all Z to the D.
Because you just subtract 1 and then you still a D plus 1 and you subtract different things.
Yeah, I mean, basically, so just like, let's say, generating this one, you just take a negative of this, negative of the last one, and then everything else is a multiple of P. So you take P1 times whatever, P2 times P2 to the PD plus 1 minus 1.
Yeah.
And so on.
is 1, so you just
I was just doing with something concrete. So I was saying you take the negative of A1 to AD and then you still.
And now let's say if you want to try to get a non-negative integer solution. So you see, let's say, look at the coordinate of this one, xd plus 1. So notice that xd plus 1 will be minus 1 modulo each of P1 to PD. Let's look at the first equation. So xd plus 1, let's take the first equation modulo P1, right? So here everything is a multiple of P1. So this is a multiple of P1, everything here is 0, so it's clearly a multiple. So you will have xd plus 1 times PD plus 1, and here this is a multiple of P1, so is equal to minus PD plus 1, which means xd plus 1 is minus 1 mod P1. In the second equation, you get xd plus 1 is minus 1 mod P2, and so on. So in particular, that means that xd plus 1 is minus 1 modulo the product. This is by Chinese remainder theorem. It's minus 1 modulo P1, minus 1 mod P2, and so on. So it's minus 1 modulo the product. And if minus 1 modulo the product, the smallest possible non-negative number that we can choose is the product minus 1. But that's too large. Because product minus 1 times this is basically P1 to PD plus 1 minus P1. And we have something left. That's not possible. And that number that you have here, the target, so the positive real solution, this y1 to yd plus 1, are roughly of the same size as the bound that we had, like slightly smaller than that. So we basically show that the bound that we have is quite tight. Okay. So what is our results? I mean, basically,
N is off, I think, right? What is the difference between the two bounds?
Two bounds, a factor of n minus d.
Yeah, a factor of n is off. Okay.
Yeah, this is this thing, right? In the n minus d. This. Okay, and for standard ILP, so if we had the standard ILP where all the constraints are inequalities, not equalities, remember that I just talked about the standard reduction. You can just interpret this. That's like basically, so if we were given this, we would just do the standard deduction and then run our algorithm. So the constraint would translate to the following. So there exists a polynomial algorithm that finds a solution to the following as long as the following condition holds. So the condition simplifies quite a bit. In particular, first of all, the lattice condition is no more needed because it's by default, because we're adding these U1 to UD that like generates the whole lattice essentially. So that's like the first D. If you think of U1 to UD as corresponding to the first D columns, then that's just the whole, that generates the whole of the Z to the D. Right? So the only thing that we need is really that there exists a real solution such that summation ai by I is not just less than or equal to t, but there is a certain gap. So the gap is n times the largest norm of ai. So it's largest L2 norm of ai.
This is a.
So
this the right hand side is a vector. Is it a scalar?
Oh, sorry. Yeah, it's like coordinate wise this number.
Okay.
So think of this number coordinate wise. Yeah. Sorry. So this vector is bigger than or equal to this times 1, 1, 1.
Okay.
That's right. And this is a sufficient condition for our algorithm to work. Actually, this I've tried to like basically we've tried a little bit. I mean, I don't think we've put in that much effort. If we can get this same thing via some other ideas, I don't know. I mean, maybe it seems quite simple. Maybe it's possible to get this statement with some other ideas. The equality statement, I think, is quite non-trivial, uses lattices, but like maybe this is you can interpret in some other way to get this, because we get something that seems quite wrong. And in particular, if you see, we don't have a delta to the d plus 1 here. We just have n times max of norm, right? Because this happens because the volume of this lattice with all like the U1 to UD vectors, there is a 1, 0, 0, 0, 1, 0 vectors. The volume is just 1 there. So we only get a contribution which is norm AI. Yeah. So this is the condition. Okay. So I'll end with open.
Wait, go back. This thing is somewhat. So what happened? Can you explain? You were trying to say this, but you didn't quite get it. Can you explain what happened to the power D?
Oh, so okay. So what I'm saying is that this power D came because we were taking the volume of this lattice generated by all A1 to AN minus 1, right? Or A1 to AN minus 1. So now the first D vectors are just the integer lattice, like Z to the D with the fundamental basis, right? So the volume of that is 1.
Okay.
So that contribution to max this to the power D just vanishes.
Okay.
Just vanishes. So we just need it once.
Okay.
And not really. So this was an upper bound, a simple upper bound on the volume.
But then why don't you just get 1? Why do you have a max?
Oh, because they like so there were two different I mean basically there was a volume and there was a length. And so you have to either get a volume of the d minus 1 dimensional lattice or volume of the d dimensional plus I mean, so it's a maximum of two terms. One of the terms has maximum norm AI and the other has maximum norm times the volume.
Okay.
But volume of d minus 1 dimensional lattice. So it's like for this problem, it translates to this. But for if you look at the other matrix that we get when we look at ILP, the standard ILP, then you'll just get max norm AI.
Okay.
All right. So open questions. There's an order n gap between our algorithms and the impossibility results. So this is true for like in some sense it's true for the unbounded subset sum as well, and also for ILP. So the question is, can this gap be closed? In particular, can Erdős-Graham be made fully algorithmic just as is? As I said, the greedy approach will not work directly. So one has to think of some better approach. I mean, it's a nice question. I mean, like whether we can make it fully algorithmic. And are there other alternative conditions? So this was So when like making the target large in this sense was one way of getting like polynomial time algorithms. Like are there other alternative conditions that make ILP easy?
Even for Erdos-Ram, the gap is still order and it's the same gap.
Right. Because what we said is that these conditions, right? I mean,
Oh, yeah, you don't have the over I minus one.
over I minus
Yeah.
1. So we can just instead of this, we can just say that if t is bigger than an squared,
Yeah,
then all of the conditions are just by default satisfied.
yeah.
Right. So that's the simplest. I mean, or an squared divided by a constant, then we are
Yeah.
still fine.
Yeah.
Basically. So, but like I mean, this is slightly better than just saying t is bigger than an squared, but still, if in the worst case, there is an order n gap.
Yeah.
Okay, so and the question is whether are there other alternative conditions that make ideal linear programming easy. And another question: can we relax our conditions and maybe have a trade-off between, like, in terms of time complexity of the algorithm? Let's say if t was slightly smaller, can we still have an algorithm that maybe does not run in polynomial time, but still is better than what you would have if you were given a general ILP instance.
But how do you ensure that the solution exists?
So then you have to talk about the problem where you want to find a solution if there exists one, and otherwise just say there's no solution, which is a totally different game. I mean, I don't know how. I mean, our results can be merged with that, but maybe there is some ideas that we can take from here to solve the general problem. Of course, here we were talking about instances where we are guaranteed that a solution exists.
Yeah.
Right. So, but in general, I mean, if the target is not that large, then you will not be guaranteed. So you have to find a way to. Actually, there the decision problem is already interesting, right? I mean, just saying that there exists.
It's NP hard.
Yeah, it's NP hard. But I mean, in general, it is NP hard. So can we have a middle ground where it's easier, but maybe still, maybe still doesn't fit in our definitions.
So this checking, so this there was old paper of Lenstra like around the same time as LLL where you showed that if you have variables or constraints bounded, then it's still polynomial time. So that's more like a sparsity kind of, or maybe not sparsity. So some like saying, but here that kind of structure doesn't show.
Yeah, I don't think so. I mean, so the variables bounded is like there are plenty of algorithms that if the number of variables is small, then the best algorithm actually runs in time, like log n to the n.
Or but here I think they want fully polynomial.
Yes.
But log n to the n.
So
n is the number of variables.
N is small.
But I think he also did this thing of number, like there was some in that paper there was both number of variables and number of constraints. So that's what I was checking right now.
Number of constraints, I don't.
Yeah, so he said that so if the fixed number of constraints also the same algorithm.
But like unbounded subset sum is just one constraint. Knapsack is just one
The
constraint.
integer unit programming problem, the fixed value of m is polynomially solvable.
So the non-negativity is that
They're also constraints. Non-negative constraints.
Yeah, non-negativity is also constraints. Yeah.
Okay. I see.
So actually, it's claiming it's the same. Okay, so it's probably just some.
Okay.
Same the bounded variables thing.
Oh.
And
I don't know. I see. So if you're allowing arbitrary.
Yes, but fixed number.
Then it's maybe just find just this lattice, like that.
Yeah,
LLL would work, right?
Yeah, that paper is actually saying that LLL implies.
Exactly.
It's like a two-page paper.
Yeah. Right. Then it works. I mean, basically what I just was saying, right? If we did not really care about everything being non-negative, then just LLL would give you a solution.
How old is this process?
No, this is the same time as
Basically, LLL, I mean, this is the implications of LLL.
Yeah, probably some people asked him when he actually write the story that some people asked him when that's
Who's this?
So if I say that if I give you some bond on your xi's, if I say that each xi is, I don't know, between 1 and 0 and n square.
Sorry, between?
Your xi is supposing I place some upper bound on them.
Right?
You can't just take too large. It has to be, let's say, between 0 and n square. Does everything you have still carry over? Do you still get Like,
xi less.
actually, I have no idea what would carry over in that case.
Wouldn't that just be, that can be implemented with just adding a constraint, right? Xi less than or equal to, so it's like think of it as introduce a new variable
Right.
and then xi plus y, like this is like introduce a new variable y and then say xi plus y is equal to n squared. Y is non-negative.
Xi plus y.
Equal to n squared
Okay.
and y is non-negative. Just introduce a new constraint. You just that's it. That's what you're saying, right? You want that xi is less than or equal to some norm like d, right?
Yeah.
So I just introduce a new constraint to my constraint that already exists, which is this.
Okay.
And I'll introduce and I'll say that y must be non-negative.
Sure. Okay. So
Now, I mean, with this new constraint,
yeah.
then this solves. I mean, and we just run the algorithm that we have. It solves your problem.
So you're saying that the same sufficiency condition holds?
Yes.
Okay. Okay.
Maybe you get something that depends on y. But you can actually, as I was saying, we can choose the first d the way we want as long as these d vectors are linearly independent. So in particular, the column corresponding to y we can keep on the right side and then we don't have any additional condition on y.
But now it is possible that there is no solution, right? If you ask for xi to be less than some b.
Sure, then it is possible.
Does it detect that?
So see, what we are having here is we have a certain set of conditions. Right? If the conditions are fulfilled, then the algorithm works.
Yes, but this is a new condition now.
This is a new condition, so one has to see how this, that depends on your B, where how this condition would translate, what you will get exactly. But you can just, this is just plugging in these values, right? No, plugging in what you get here in terms of the volume of this lattice. So I mean, so what I said here, this condition. So if you want to be really careful, actually in the paper we have slightly different condition. We talk about the volume of the lattice.
So like you,
Even
let's just say for the subset sum, right? Even let's say for the subset sum problem.
Yes.
How would the conditions change?
In the subset sum problem, now you want to add this constraint.
Yeah.
Then you will translate it to two-dimensional problem where you have two constraints instead of one.
I would translate to.
So now you have, so you had the subset, the unbounded subset sum where you have given a1 x minus a2 x is equal to t.
Yeah.
And now you will introduce this new one, right? So you will talk about the two-dimensional problem now and check whether the condition that we have for the two-dimensional problem that holds. Then we get a solution.
Okay.
So one can debate how reasonable the condition is.
Sure. That's right.
This is like, but the algorithm works as long as this condition works.
Okay.
Right?
Okay.
So one has to work out whether the condition holds, and basically there is some flexibility there here because we can choose our first d vectors the way we want, so that then we have a certain condition on these first d vectors, and depending on how we choose these first d vectors, we might have so the condition might be fulfilled, for example, for some choice of the first d vectors, but not for the others, and then we might want to kind of permute these vectors.
No, once you put that constraint, everything like none of this holds, right? Because we don't even know if it is possible to find x's. Like say b, so b is equal to 1.
Okay. See, we get a condition, use linear programming to check whether that basically that condition actually holds or not. We get a certain condition, and then we see whether there exists real y1 to yn. That I cannot do by hand, right? I mean that we can basically run a linear programming algorithm to basically check whether that condition holds. If it doesn't, then then this algorithm cannot promise it. If that does,
that works, then we can plug it.
yeah, okay.
So if you're dealing with constraints, you make sense that there is no solution, then you will be able to have it.
Then also it's it.
Yeah. So we plug in the plugin, get constraints, get the corresponding linear program, check whether there exists a solution. If there exists, then this will find. If it doesn't, then basically our precondition does not hold, then we cannot really get a solution. Right? So there is no easy way to check this last condition except by running the linear programming algorithm.
Let's thank Divesh. Any more questions? Okay, so what I wanted to say is that Divesh is here for today, tomorrow, and Friday. He's sitting in 8207 next to my office. He's a man of many talents. He does complexity, he does crypto, he does lattices, he does storing theory. So whatever your problem is, he probably has an answer. And if you impress him, you may just earn an all-expensive paid trip to Singapore. So do talk to him. Make sure he's busy. And yeah, let's thank him again for coming.
It's not that expensive.
To go to Lucknow.
Yeah, that might be true.
Mumbai, Singapore might be cheaper.
Any character also.
I told you.
Yeah, it's fine.